So have you ever actually stopped to wonder how a computer, a machine built entirely on absolute ones and zeros, can understand the wonderfully vague, imprecise way that you and I actually communicate? I mean, we constantly say things like, it's a little chilly, or he's somewhat tall, and somehow modern systems know exactly what we're talking about. Well, in today's Explainer, we are diving into something truly fascinating, the humanization of machines. We're going to look at how these systems act as the ultimate translators, finally learning to understand human vagueness through a mathematical process called fuzzification. It's this brilliant bridge between human intuition and machine precision, and honestly, it is a total game changer. Let's get into it.
Here is our game plan for today. We'll start by comparing crisp and fuzzy worlds, then quickly contrast fuzzification with defuzzification. After that, we'll explore words as linguistic variables, dive into the actual math of fuzzifier curves, and finally look at how we modify all of this using linguistic hedges.
All right, part 1, crisp versus fuzzy worlds. How we move beyond just ones and zeros.
To really understand how these machines think, we first have to look at the massive limitation of traditional two-valued logic. The classical computing world where everything is sharply true or false. A variable is simply a 0 or a 1. If something doesn't fully belong to a set, it gets completely thrown out. But let's be real, the real world almost never works in absolutes. Think about an apple for a second. If we use crisp sets, there's a hard, undeniable line: it's either an apple or it's not apple. But imagine you're holding a perfect apple and you start taking bites out of it. At what exact millisecond does it cross that strict boundary to not being an apple anymore? Is it when you're halfway done, or maybe when you hit the core? Crisp logic completely falls apart here. But with fuzzy sets, the object gets to make a smooth transition. It can actually belong to both the apple and not apple sets at the exact same time, evaluated by specific degrees.
And that brings us to this incredibly cool concept called possibility distributions. Instead of strict, rigid cutoffs, possible versus impossible values are evaluated by degrees. Let me give you a real-world scenario. Imagine the police are searching for a suspect who is, quote, between 20 and 30 years old. If a computer system uses a crisp set, a 19-year-old is a 0% match. He's entirely impossible as a suspect just because he falls 1 year outside that hard bracket. But a fuzzy possibility distribution, it provides a smooth boundary. It actually recognizes that a 19-year-old is, well, practically 20, granting him a partial possibility match of, say, 0.75. It evaluates reality exactly the way a human detective naturally would.
Moving right along to part 2, fuzzification versus defuzzification.
So how do we actually get the machine to perform this translation? Well, for a fuzzy system to interact with the real world, it requires two massive operations. First, you have fuzzification. This is the process of converting precise, crisp data into imprecise, fuzzy data. It's actually pretty easy computationally and relies mostly on simple if-then rules. On the flip side, you have defuzzification, which is the exact opposite operation. It reduces that fuzzy set back into a distinct, crisp number, so a physical system, like a motor or a voltmeter, can actually act on it. And defuzzification is computationally complex. It relies heavily on advanced math, using things like center of gravity or centroid methods to find the final physical outcome. But for the rest of this explainer, we are going to focus entirely on that first, absolutely crucial engine, fuzzification.
Part 3, linguistic variables. This is where we start using actual words as variables.
To understand how fuzzification works, we really need to zoom in on the vocabulary. Instead of strict numerical values, we assign words to variables to capture how people genuinely think and make decisions. I mean, we don't naturally say, the motor is running at exactly 95 degrees Celsius. We just say, whoa, the motor is running really hot. So in fuzzy logic, temperature becomes a linguistic variable, and it takes on linguistic values like hot, cool, warm, or comfortable. It embraces the fact that our lexical imprecision is actually a highly useful feature, not a bug, when we're trying to solve problems.
Now, to formally structure this for a computer, we use a specific framework. Okay, don't let the math here intimidate you. It's actually super straightforward. Let's break it down. Big X is simply the symbolic name of the variable, like height. LX is the set of linguistic values it can take, right? So short, average, and tall. Then we have the Greek letter chi, which represents the physical domain of crisp values, meaning the actual hard measurements, like 150 to 210 centimeters. And finally, mu x is the fuzzy function. This is the actual math that maps the words from LX right onto the crisp measurements of chi. It is the literal translator of the system.
Part 4, fuzzifiers and mathematical curves. let's look at the actual math of translation.
That final symbol we just talked about, mu_x, represents mathematical membership functions, or what we call fuzzifiers. Gaussian and generalized bell curves are incredibly popular methods for doing this. And you might be wondering, why? Well, aside from their concise notation, it's because of their absolute smoothness. Both of these curves have the massive mathematical advantage of being completely smooth and perfectly non-zero at all points along the domain. It allows for this beautifully symmetrical, totally seamless transition between states. But because Gaussian curves are perfectly symmetrical, they do have a slight limitation. They can't specify asymmetric membership functions, which, as it turns out, are critical in a ton of real-world applications. That is exactly where sigmoidal curves step in. These curves intentionally open to either the left or the right. Plus, if you ever need an asymmetric closed function, you can literally synthesize one just by taking the difference or the product of two different sigmoidal functions. It's incredibly clever. And finally, we have polynomial curves, which account for several other vital functions. And these are named strictly for their shapes, which makes them easy to remember. The z-curve is an asymmetrical curve that opens to the left. The s-curve is its exact mirror image, opening to the right. And then there's the pi curve, which drops to 0 on both extremes but features this prominent rise right in the middle. By using these different shapes, a system can map out completely unique, highly specific types of human uncertainty.
Part 5. Modifying with linguistic hedges. This is where it gets really fun. Okay, so we have our variables and we have our curves. But let's introduce the actual grammar of fuzzy logic. We've established how a computer understands the concept of tall. But how on earth does a machine calculate an abstract, emotionally driven word like very, or somewhat, or extremely? I mean, how do you mathematically quantify the phrase sort of? The answer is linguistic hedges. Hedges are terms that modify or qualify the shape and position of a linguistic variable's curve. And they do this primarily through two mathematical operations. First is concentration, or intensification. This essentially narrows a fuzzy set, allowing for modifiers like very or extremely. The second operation is dilation or diffusion. This widens the curve's boundaries, which perfectly captures words like somewhat or more or less. And the mathematical punchline here? It's beautifully simple. To make a machine understand the word very, it literally just squares the original membership value. That's it. So if tall has a value of 0.5, very tall becomes 0.25. It concentrates the likelihood. And if you want to say very, very tall, you just raise it to the fourth power. On the flip side, the word somewhat is calculated by just taking the square root. If tall is 0.81, somewhat tall is 0.90. It dilutes the curve, spreading it out. Let's put the whole shebang together and see how this builds a complete system. Take the linguistic variable age, for example. That's our base concept. This drops down into primary values like young or old, which each have their own baseline mathematical curves. But then, utilizing hedges, those primary terms branch out even further into concentrated versions like very young or very old, utilizing those exact mathematical shifts we just talked about, like squaring the values, to narrow the curve tightly around specific age ranges. We can literally build an entire tree of nuanced human language from just a few simple math operators.
So what does this all mean for us? By combining words, curves, and hedges, machines can seamlessly navigate our incredibly imprecise reality. They translate our ambiguous human desires into exact mechanical actions. From the high-performance drives in electric cars smoothly adapting to very rapid dynamics, all the way to your washing machine deciding if a load of laundry is somewhat dirty or very heavy, this invisible mathematical translation is constantly happening all around you. So I'll leave you with this final thought. Which appliances in your home right now do you think are using fuzzy curves to interpret your vague human behavior? Thank you so much for joining me on this explainer, and keep questioning the math behind the magic.